Welcome to lecture 7. So, on the PCP theorem, the main focus today will be to construct two prover PCPs or rather two query PCPs, which are also called label cover in the PCP literature. And then we'll talk about one of the major topics in interest in PCP thing called the parallel repetition theorem. So let's quickly recall where we are. So by the end of last lecture, we had already proved the PCP theorem, which basically states something like this, that there exists constant P and Q such that SAT has a PCP verifier which tosses at most C log n points, and based on these C log n points, probes a proof in at most Q location, and based on this Q locations, either accepts or rejects the proof. In the yes case, it accepts the proof. There exists one such proof file which causes the verifier to accept with probability 1, no matter which random point it tosses. In the no case, for at least half the random points, the verifier notices the inconsistency among the, no matter which proof you feed to the verifier notices the inconsistency among the locations and rejects based on those. So we gave this alternate characterization of NP. And
it should be 3 SAT, right?
Any SAT. Why not?
Because for the process, you need to algebraize and you need to.
But you have a reduction from SAT to 3 SAT. You can first run the reduction. Yeah. Alternate characterization. This statement is true for any NP. Which the only thing that will differ is the constant C will depend on which NP complete, which NP language and NP are talking about. Now, okay, so this is, if you recall, go back to the very first lecture, one of the uses of applications of the PCP theorem was for hardness of approximation. So we will use this just like SAT being NP complete was the starting point for several of NP complete list reductions. This will be the starting point for to prove several hardness of approximation statements. But as nice as the statement is, this is not in the nicest form. A nicer form will be in which the number of queries are made as minimal as possible so that you don't have to deal with one. So we'll ask if we can transform this object into actually another object in which the number of queries is as small as possible. And in this context, you would have seen the first problem that if you want the queries to be the alphabet size of the proof to be over binary, over bits, you cannot make the queries any smaller than 3. PCPs over binary alphabet, if they require only 2 queries, they actually collapse to P because they will capture a 2 SAT problem. Then my predicate will be 2 SAT, it will collapse to P. So if you want to work over the binary alphabet, you have to go to 3. You have to go to at least 3. We haven't yet seen how to go to 3 query object at this point. In fact, that will be the main result for the next lecture a week from now. But if you don't have this restriction of Boolean, the alphabet being Boolean, it's conceivable that you can go down all the way down to 2 queries. And we in fact saw this. We saw that there's a 2 query format, there's a 2 query representation of this. There's a 2 query version of this in which you ask one proof. So it can be said as there are 2 provers. You can, instead of saying the 2 queries are in the same proof, you can talk of there will be 2 proofs and you ask one proof, you probe one proof for one query and another proof for another query. And how can you convert this into, and in fact now because it's just one query, you can think of it as a prover. You can think of V, which on input sign, phi, and its random coins. Both these. It asks the first prover P1. We sort of saw this all the way. All the Q queries. It says these are the Q queries that I have, that I would have made into the PCP. It just asks the Q queries all of this. And another prover P2. A random query among these Q queries. And then it does the most obvious thing. This prover will answer with some local view. This prover will answer with one symbol. The verifier accepts. If the local view is a, so this is verifier 2, call it, and let's call this verifier 1. Verifier 2 accepts if local view is an accepting if the following two conditions are satisfied. If 1, local view from prover 1 is an accepting view for the verifier V1. V1, had it seen these Q queries, it would have actually accepted. And 2, P2 is answer is consistent with P1.
But this is Q plus 1.
It's not Q queries. The Q queries are asked in one shot. It's asked together. So it's asked. I just give you. I'm not asking you Q queries in sequence. I'm giving you this tuple and say, give me the answer for all of them. We are increasing the alphabet size by a factor.
The alphabet size is 0 1
0, whatever the old alphabet was sigma, it now becomes sigma to the power of u. For the first prover, the old second prover is P2.
They could have done this with a single prover. We didn't need 2 provers.
We didn't need, in the sense.
And this. So suppose you give me a PCP verifier of the first kind.
Yeah.
So I want to do this. I want to construct another verifier which does this with 2 queries.
Yes.
So you just the accepting proof that the verifier V1 will accept will expect would be.
So one will be for every Q tuple it has this one other one. But it's just, huh? And so the proof now consists the proof for V2. Okay, what you're stating is the proof for V2 will consist of 2 types of proofs. One is the old proof pi itself, which is what you're probing into P2, and the other is for every Q tuple of this one you give. So you could think of it as one long proof, but once you have non-adaptive K probes into a proof, you can think of this as K provers and you're asking them, because essentially a prover is nothing but if you're just going to ask a prover one query, a prover is just a truth table. Because it's whether I draw this picture or I put a proof, if it's just one query, a prover is a truth table. That's all. A prover is just for every possible Q queries, he has the answer. So the prover is going to answer this. Only if adaptive things change, because then the prover has memory of what the first query was could answer. So this is just a more succinct way of I don't even know if it's succinct. It's traditional. If you talk about two provers, you draw it in this format rather than in the other format. Okay. And by the way, this we already saw this. We saw the other translation.
So here the soundness will be 1 by Q.
Yeah. So what did we see? What is the soundness of this prover? So completeness is just transfers over. Completeness, V1's completeness implies V2's completeness. And for soundness, how does soundness go?
The original soundness plus 1 minus 1 by 2.
So so the original sound. So you could always assume P2 is answering according to some proof, fixed proof. Now this proof is going to commit a whole bunch of this proof is going to make a whole bunch of errors, because it's going to accept only with probability half. Therefore, half the local views are going to be half the honest to God local views will be rejecting views. Now P1 could have actually sent that and said this one, in which case you accept, but it's in P1's interest to actually always give an accepting view. That is even this one. So assume P1 always gives an accepting view. These, for at least half the time, this accepting view is not what the accepting view in the proof is. And there, if you were lucky, you could have picked up the one guy which was the different. At least this accepting view should differ from the accepting view in the proof at least one location. Therefore, what is it if let pi be the proof, P2 answers according to we know that probability over the random points V1 when it probes into pi equals accept is less than or equal to half. This would imply that probability over random points V2 when it talks with P1 and P2 phi is accept will be how much? It could be for the half the guy you give it up completely. For the other half,
1 minus 1 by P.
is that right? Yeah.
Or 1 minus 1 by P. 1 minus 1 by P.
What does that come to? 1 minus 1 over.
So not only you have to, let's say to get it to a constant.
Okay,
Okay, no, Q is constant.
Q is constant, so this is okay. But recall, I just want to make constant. So this is because we assume that the outer guy was just, we assume only soundness of the outer guy. But suppose the outer guy was actually robustly sound, then there is no, then the robust soundness just transfers over to the soundness of this object. So,
Yes, suppose I want a X soundness level of 1 by E,
mhm.
then I would have to repeat this 2Q times, right? So the identity is that to the same. So we need robustness.
But when you repeat it once, that's the whole catch. That's what I'm going to spend most of lecture. When you repeat it, does it remain 2 query? It becomes 2Q query.
Yes.
So, but I want to repeat. So we come to that point. What does it mean? So right now, I only care about some constant soundness. That's going to be the whole goal. How to improve this number. That's going to be the focus of all of today's lecture. So suppose the outer one was robust soundness of V1. That is probability that over R that the distance of pi, the local view from an accepting local view for R is at least. So let me not write this. I want a robust soundness of V1 implies soundness of V2, and in fact, without any deterioration with respect to Q. And by the way, this is a transformation we already saw. That is for the line point test. That's if you view it as a line point test, that was a two-prover object. And if you viewed it as a single thing, reading it, that was the robust version of it. So we in the past, when doing the notation test, we saw this translation. And what I'm doing is the other translation. And if they both, and if this had robust soundness, then these two are actually the same viewpoint. All I want to claim is for sometimes it might be useful to have this two query version of the thing. And why is the two query version useful? The two query version, now you can think of it as a graph problem. The two query version, the two query PCP. You can think of every query of the first prover as sort of some vertex, say U1, and this is W1. So U1, so there's no U1, U1 W. U is, or let's call it U1 and U2, where UI.
Robust soundness of V1 would have meant that not only does V1 reject, but the view that the answer that V1 gets is far from any accepting configuration.
Yes.
And
So depending on how you phrase the robust soundness, if you want, there are two ways. We stated it as probability that the local view is far. You could have said it as one expectation. Expected distance from the accepting view is so much. If we write it that way, that's exactly this one, the soundness of this object. If I write it as, if I write the robust soundness, this is not the way we wrote robust soundness. If you write it as expected distance of the local view from an accepting view, that's exactly the soundness of the two query object. Then there is no loss in translation.
So this 1 over Q is because maybe you just edit the E2 sends a view that's corrupted at just one location.
Yes.
That's fine.
Yeah. We won't need this fact right now because for us, U is the constant, all of this won't matter. Later on, it will matter. U is the set of all possible queries to prover PI. How large are U1 and U2?
2 power I.
2 power the number of randomness, which is how much? Which is polynomial.
N power I.
N power order 1. So this is something we can actually write down. And I'm going to put an edge between U1 and U2. So I'm going to construct this bipartite graph. U1, U2 with edge E, and U1, U2 belongs to edge if there is a particular random point on which you query this query and this query. If you do that, I'm going to put this edge between. If there exists a random set of coins or such that V2 queries P1 and P2, the queries V2 queries U1 and U2.
So the length of the left side is the length of the proof and the length of the right side is 2 power I.
Yeah, at this point of time, I have completely forgotten. There are two provers in the random points. I have a two prover proof. So I had a single prover proof system, a Q prover PCP. We have moved from it to a two prover object. And from the two prover object, I am constructing a graphical representation of the two prover object. And what are we asking now? What is the thing? We are asking basically, you give me a coloring to the left side, you give me a coloring to the right side, and certain colors or pairs of colors are accepting if the verifier is going to accept that pair of colors. So there is a sort of so this guy is going to get, so there are two colors here, let's call it sigma 1. Sigma 1 is actually what the old alphabet to the power Q, and sigma 2 is the old alphabet itself. What we are asking the provers is actually A1 from AI, from UI to sigma I. And you're asking, does there exist such a coloring? So for now, every edge, so you're asking, the question which we are going to return is the following. And there's a predicate, and for each edge, U1, U2, E, there's a predicate phi E from sigma 1 cross sigma 2 to 0, 1. There's a predicate which is basically whether the verifier will accept if he sees this answer and this answer, the two objects. You can now ask this, and now you can now state the following question. You can ask, so the input, so the instance now we have completely phrased it, transformed it to.
Sorry, there is a predicate that's independent of the E, isn't it?
Huh?
So, but you have to check if U1 matches the position.
It depends. The predicate would be independent of, sometimes it could be, but here it is very much a
Which location?
which location and all.
And it also depends on U2.
The predicate doesn't depend on the location.
Yeah.
No, it doesn't depend on U2. It depends, the predicate,
You want.
no, the predicate, no,
So,
the predicate depends on the two queries being asked.
so I should think of U1 and U2 as just locations,
Yeah, you want you to are the location.
and sigma is the thing that.
Sigma is what is being returned there. So, that's very, very important. UI is the set of possible queries, so it is just the set of locations. Sigma is what the prover is going to answer for those locations.
So I will then just take this that the first component is an accepting view and the second component position matches.
Matches this.
That
That's all that it does. So the instance is this. So we're going to come up with a new instance, a problem instance, which has this long thing. It has a bipartite graph. It has two sets of colors, sigma 1 and sigma 2, and a set of predicates for every edge. And the value of this one is the max over all assignments AI from UI to sigma I of the probability that phi, if you pick a random edge, phi E of A1, U1, A2, U2, you pick a random edge, U1, U2 equals 1. But I actually done nothing. I just transformed the two query PCP into this instance. This is just a syntactic transformation. And this is what is called a label cover instance. And an alternate way of stating PCP theorem is the following. There exists. Let's define what I'm going to call gap CS label cover. The S instances are those instances phi such that val phi is greater than or equal to C, and the no instances are those instances phi such that val phi is less than S. And label cover just states there is a polytime reduction from SAT to gap 1 minus epsilon, let me just call it label cover, with constant sized alphabets, sigma 1, sigma Notice nothing has happened over here. So actually, I should state this. State it this way. There's a point. There is there is a there exists an epsilon in 0, 1 such that the following holds. Particularly speaking, there exists an epsilon and constant size alpha at sigma 1 and sigma 2 such that the following holds. Those are independent of the instance. But all of this are just different languages of representing the same PCP theorem. I have done nothing from moving from the Q query object to the to query object to the label cover. These are all syntactically the same object. In fact, if you are working with robust soundness, expected robust soundness, they are exactly the same object. Otherwise, there's some deterioration from one constant to another constant along the way. And the reason this formulation is a little nicer for hardness of approximation reduction, usually it's nicer to have a reduction statement rather than in language of proof verification and all. So when we try to prove the PCP theorem, we use the language of proof verification. When we are going to use it for hardness of approximation, usually this is the starting point. It moves from one language to another language, and the language that we will start off with will be label cover instead of from SAT. Gap label. Is okay? So the question which we're going to ask is now, today is, can I make this 1 minus epsilon arbitrarily small? Can we improve? The question is, the focus of today's lecture is going to be can we improve the soundness of the target label cover instance in the above reduction? That's going to be our main focus. Notice, so suppose we wanted to already get this object, that means we should have gotten a. So firstly, we can't oppose this loss going from Q query to two queries this way, because that is going to have, it's going to push the soundness all the way to 1. But we notice that if you actually prove that expected robustness of the PCP we constructed with, that's not a loss. So one thing is we could have started off with, we could have tried to construct PCPs whose expected robustness was very, very good, and then this object would, so that's one way of constructing it. This was not how the original PCP. In today we do have PCP constructions where directly using algebraic constructions you can construct a PCP whose expected robustness is as small as we want it to be. You tell me delta and I can give you a algebraic PCP construction whose expected robustness is as small as delta. This is not the PCP which we constructed this time. If time permits, we will come to this construction later on. So this approach will not, that approach will not work. Another is, now that we have this reduction, can we do something to, can we massage it to improve the soundness? And one natural way to improve soundness that we are very used to is just repeat. So the two possible options, two possible routes. And one is construct PCPs with very good expected robustness, robust soundness. The other is
when very expected.
Very
expected.
With very good. Should ask what that is also, but not what that is. Massage above reduction. To improve Fondness. And today we will be doing two by our repetition. So we want to repeat it. So suppose you took a 2-query PCP and you repeated it k times. The soundness was, if it was C before, it's going to drop to C power k. Sorry, if it was S before, it's going to drop to S power k. But on the other hand, a 2-prover PCP, if you repeat it k times, it becomes a 2k prover PCP. It's not, doesn't remain a 2-prover PCP. So repetition the k repetition does improve soundness. In particular, S goes to S power k, but so that's the good feature of this. But on the other hand, 2 provers or 2 queries becomes 2k queries. And somehow I would like to stick in the format of label cover. I don't want to go to 2k plus. So in those cases, I'd have to talk about hypergraphs rather than this one. I would like to do this. So the question is, can we still stick to two queries and do it? So a natural suggestion, can we repeat maintaining the 2-query structure?
So now we have to blow up the alphabet.
You are allowed to blow up the alphabet. So think of k as just a constant. You just need to repeat enough times to get 1 minus epsilon to 1 minus epsilon is like 0.999. I want to get it to 0.001. So usually if you repeat it like 100 times, this will suffice to get it. So think the k is constant. So moving the alphabet from sigma to the k is not something which I am going to be concerned about. Question is, how can we do this? And one suggestion that was told was actually repeat in parallel. So parallel repetition. And that's going to be the focus of the rest of today's lecture, both the first part and the second part. Does parallel repetition work? Okay. So, because I'm going to spend a lot of time, let's restate the problem this way. So I'm going to talk about, we have a single game. This is either you view it as a label cover or a 2-prover thing. And the game is specified by what? The game is specified by a verifier. The game is specified by a predicate mu on questions U1 cross U2. The game picks up a pair of queries. So you think of V, it samples. So now I'm going to move to language Q1, Q2. It samples from U. That's the first step. And it sends Q1 to the first prover P1, Q2 to the second prover P2. And there is and they return answers A1, A2. And you accept if there's some predicate of.
You sample a random edge. You don't sample a random pair.
A pair is there's an underlying distribution on U1 cross U2. That's what is specified.
It's specified with the edge.
The edges, yeah. The mu is, this is the edge distribution. Edge distribution and predicate pi by E for each edge. So the game, I'm just using various languages notations because this object is called sometimes to prove PCP is called a game, it's called a label cover. In this language, it's called this way, and you accept if this predicate phi of Q1, Q2 of A1, A2 equals 1. Okay, so that's and the value of the game. Value of the game is what? Is you want to come up with the best strategy for the provers. That is, you want to find the value of the game. You want to say a strategy for the provers. Strategy for provers is phi 1 is something from U1 to sigma 1. Phi 2 is from U2 to sigma 2. We're going to change this a little bit. We'll assume that this is assuming the prover strategies are deterministic. We could assume that the prover strategy is randomized. That is, if U1 cross R, there's a common random string that they share. The two provers. So this is sort of a random, there's a common random string. The strategy for provers to maximum, what do I want to maximize? To maximize the following.
By averaging, is it?
Averaging, it is the same. They are the same. They're the same, but there's a reason I want to write it this way of phi E of phi 1 Q1 comma R, phi 2 of Q2 comma R. We will call this quantity. The value of the game omega of G is just going to be max over all phi 1 and phi 2 that have this property. Value of the game is what we omega G is what we call the val of the instance. Now, what is the parallel repeated game? The K parallel repeated game. Denoted as G tensor K, to say that's been repeated K times. It's just this, the verifier now picks for each J in 1 to K, it picks Q1J, Q2J, it picks K copies of these. Queries P1 with Q11, Q21, all the way up to QK1. It sends all the queries in parallel. It sends this whole vector Q11, Q12, Q1K. And similarly, it does the same thing for code. 1, 2, 2, 2. Receives answers A1, A2, AK from P1 and B1, B2, BK from P2. It's going to get picture is going to get A1, A2, AK. And accepts if for all J in K, phi of EJ, this is what from EJ, EJ of EJ BJ equals. The most natural thing is just still far very verbose written, but this is exactly what one would mean if they say the K value.
So all the values are true.
All the values are yes. You can talk of threshold games also, say at certain fraction, but let's talk about all the values. This is sort of like RP amplification rather than VP amplification. And the question for us now is going to be basically, how does omega G tensor K come versus omega G behave? That's going to be the focus.
How is it different from just giving key queries to understand?
Yeah, so this is exactly what Fortno, Rompel, and Sipser. So parallel repetition was during Sipser's PhD, during Fortno's PhD, when he was working at Sipser, they sort of. So if you had sequentially repeated it, it would just, this would just be, they just assumed this. Mistaken. And went ahead with, said you could reduce the soundness of a two-prover system arbitrarily by doing this. And very soon, Lance himself and Lance Fortno came up with a counterexample to this. What we will see today is, but then Lance Fortno then came up with a counter example to above statement. The thing, and basically all these counter examples in the sequential repetition, what are we assuming? We are assuming that whenever you are answering a particular query, you answer that query. But now you get to see all the queries in advance. So you can answer the first query based on questions to the second or third query. Question is, why does this give you more power? It should feel it shouldn't give you more power because the queries are independent. But it can give you, that is, you need to argue that this doesn't give you more power. And in fact, what we will see right now, we'll give a counter example, which is a counter example to that statement. I will show an example of a game in which I repeat it 2 times. The value of the game will be half, but when I repeat it 2 times, the value of the game will continue to remain half. And the reason is going to be, basically, I give a strategy in which the provers will use the queries to the first round to answer the second round and vice versa. And somehow that fact tells you that this is not going to be an easy thing to do.
So the fact that the prover can see all the queries at once.
Yes.
So that's the difference between this and what we would have done otherwise. Right?
Sequential repetition is committing to the answer. After seeing I queries, he's committing to the answer of the I query. And the ith answer is committed after seeing I queries. It doesn't have the ith answer could depend on all the previous, but it's committing. It doesn't look ahead. And you can show that this one will only, if that were the case, it's omega G to the tensor K is actually equal to omega G to the power K. That's easy. Here, he can answer the first query based on questions to the second query. This might seem this one, but let's see counter example.
But on a PCP, proof has been fixed before that.
But or not as a PCP proof has been fixed. So that will mean 2K, there is a 2K query object. I want to view it as a 2 query object. If I want to view it as a 2 query object, you are writing a whole 2K tuple. You're writing a K tuple over there for each query. So there you're allowing the prover to cheat now. You're allowing the prover to answer the 10th query based on the 100th, give an answer to the 10th query based on the 100th query's question and stuff. Let's see the counter example, then it should be clear how the prover can cheat. We'll see Fege's counter example. So let's call this game F. Again. In fact, this is going to be a free game. It's going to be a game in which the queries to the two provers will have no correlation between each other. They'll be independent queries, but yet you will. These are called free games. We will not study them, but they form an important. I guess counter example. The game goes this way. So the verifier B. So there are two provers. It will be convenient for me to call them B0 and B1 for notation. You will soon see. The verifier first picks B0 and B1 independently, uniformly, and two uniform bits. Okay, just going to pick two uniform bits and send, and does the obvious thing. Is going to send, the queries are just going to be bits. Going to send B0 to the first prover and B2 to the second prover. Send BI to prover PI. Okay. The provers are going, the answers are going to be 2 bits each. So each proof, the questions are 1 bit each. The answers are going to be 2 bits each. They are going to send C0, D0, C1, D1. Receive answers. CI, DI. From prover PI. Now I need to say what's the acceptance predicate. When does the verifier accept the pair CI/DI, the pair P0 D0 and CI/DI? Accept if the following holds: C0 D0 equals C1 D1. Firstly, these both, the two answers are the same answer from the two provers, in which case let's call it CD. Say CD. Prover PC received query D. So you do this if firstly they both should be giving the same answer, and you interpret the answers as the first bit of the answer telling about which prover got which are the provers, and the second bit telling you what did that prover get. So you accept if they are both talking about the same prover. They are both going to be talking about prover C, and they say that prover C received question D. Only then do you accept. Notice that this value of this game is half, because one prover has no. If they both have to talk about the same prover.
What is PC?
Huh?
Okay.
PC, the prover PC received query D. Notice that the value of this, it's easy to cheat, easy to see. Omega of F is half. Because one of the provers has to be talking about something they did not receive. And they can only make a random guess. Okay, so it should be easy to see omega f. Now I want to ask what happens for omega f when I tensor it. So once again, what's the setup here? The setup here is now the game P. I'm talking about the game. Let's cancel 2. Let's prove P0, P1, and he gets B10, B20, and he gets B20, sorry, B11, B2, and they return 4 bits each. And I want to say the following, consider the following strategy. The prover P1 on query B10 and B20 returns. He has to return 4 bits. What he's going to do is, so he has to return one thing for the first round, 2 bits for the first round, 2 bits for the second round. The first round he's going to be talking about prover 0, and the second round he's going to be talking about prover 1. First round, if he's talking about prover 0, he knows what to give. He has to give B01. That's his best way to. Second one, he has to guess. What he's going to do is he's just going to give B01 again. He ignores the second query and uses the first query to answer. That's how prover 1 is working, and prover 2 does something very similar. Prover P2 on query B0, sorry, B11, B12 returns. Now, given that this is a strategy, they both should be certainly, he should say return 0 on the first thing, and they should be talking about the first prover in the first round and the second prover in the second round. Certainly, he can answer correctly for the second round, P12, and he's just going to put this over here. He's just going to use the same answer for the first round. What's the probability that this accepts?
So the condition is prover PI receives 20 PI.
The prover PI receives query BI, and he gets 2 rounds of it. So he gets BI1 and BI2.
So the PIs of both the rounds must match.
The BIs of both. So there are 4 bits being produced. All that I require is B12 should be equal to B01. It's only that match that should happen.
Yeah.
That's just a probability half. For those inputs, you are going to verifier will accept with probability half. So what's the probability that the verifier accepts? For this strategy, For this strategy, probability V accepts is exactly probability B10 equals B21, which is equals half. That is omega of F tensor 2 is at least a half. It could be better. Notice it's at most a half, because when you tensor k times, it's at least, it's no better than the just over. If you tensor k times, it's no better than tensoring k minus 1 times. Because they could have, if you had a strategy for k2, the proof could independently have been using common randomness, extended it to k, and the answer it that way. So certain this will actually show you that in fact, omega f equals omega. So what we have now, we have half is greater than or equal to omega f tensor 2, which is less than or equal to omega f, which is equal to half. So this is a game which actually, when you repeat it twice, the game value of the game does not drop. When you're looking at the quotient, you see the provers are using questions to subsequent rounds to answer the current rounds.
What happens if you repeat it 3 times?
If you repeat it 3 times, the value goes down to 1/4.
2 messes.
So that's the best correlation you can get. And Feige actually, so Feige came up with this, and Feige actually proved. Omega of f tensor k is exactly omega of f. So that's half. It's half to the power. So every second round is useless, because you can do exactly the same strategy. So there is certainly we know that omega f tensor k is at least half to the power k by 2. We know this. And what Feige shows is you cannot do better than that.
So it doesn't, so the exponent is not k but k over 2.
So the exponent is not k but k over 2. So this shows you that at least for this game, prior repetition is true. It does go down. When you repeat it, the value of the game does go down, but it does not go down the way you wanted it to go down. So the question is parallel repetition true, or is this a property of the game? Do some games have parallel repetition, or some games have? No matter how many times you repeat, the value of the game does not. You can come up with games. For every k, you can come up with a game such that for the k rounds, there is no the repetition, but from the k plus first round, there is no drop in the value of the game. But from the k plus first round onwards, the value of the game keeps dropping.
So 2 can be enlarged to
2 can be enlarged to, and there's a whole paper by Feige and Verbitsky who give a whole family of counterexamples and of this type. And basically they show this, that is.
what kind of statement can we go for general games in the light of the
Yeah, firstly, the question is, I fix the game now. So in all of these constructions, I tell you k, and then I give you a game. I give you a game such that for the first k rounds, the value of the game doesn't reduce. So the thing which you can ask is, for every fixed game, does it eventually begin dropping?
And once it starts dropping, does it drop?
So then you can first ask, does it eventually begin dropping down? Then you can ask, is the rate of dropping polynomial? Is the rate of dropping exponential? What is the rate at which it drops down? Right now, for our question which we cared about, if you just wanted to make 0.99 into 0.001, all that we care is it drops down. Actually, that's not fully true, because you need to repeat the game k times to drop it down to this. That k should be a constant, because that's your randomness is now going from log n to k log n. You can't afford k to be super constant. Notice the game is not a. So in this setting, so it's you have to be careful about this. Typically, when we talk about games, the game is a constant sized object and K is the only growing parameter. But for us, the game itself is not a constant size. The game itself is a poly in N. So you want the growth in K to be sort of, you also care that that K is not a function of this N. There is a large enough K at which point the drop in happens. So we actually want a pretty strong statement of the thing. It's not, if the order of quantifier is important over here. For our application, we need it to be, but to begin with, we can ask for every game, is there a K at which it begins dropping, after which it begins dropping, and then you want to understand the rate of decay. By the way, so the focus of this lecture is going to be proving the statement. So what was known for this historically? So the question which we're going to ask, question is, does the value of the game, yes, omega g, you turn k, dk with k, and the first of the result is due to, there are several results in this. The first is due to Feige and Killian, where they show that the value of the game does drop and it does drops polynomially. That is, basically they show for all G, so they show that for all values of G, for all games G, and for all, as long as value of the game was bounded away from 1, and the game had a constant size alphabet, then the decay of the game was inverse polynomial.
It is less than equal to 1.
Yeah, when I mean this, I mean that's fine. By the way, and this is good enough for our applications. For what the question we asked, this is good enough. It moves to 0.99 to 0.001. But very soon after Feige-Killian, Ross proved the following. And in fact, so this is called Ross's parallel repetition, because the main theorem which we are going to prove is the Ross in 96 showed that for all games G, let me write it this way, for all epsilon and for all epsilon and 0, 1 and C which is greater than or equal to 1. C, think of it as the alphabet size. There exists omega G is less than or equal to, and for all games G, omega G is less than or equal to implies omega G tensor K is less than or equal to 1 minus, I think. Epsilon 500 to the power epsilon 32 n by C. Sorry, K by C.
C is an absolute constant here.
Hmm?
C is an absolute.
Not necessarily. He says, you give me a C, and this will be a function of the rate of deterioration only depends on the value of the game and the alphabet size of the answers. It doesn't depend how large the actual game. The game could be a growing function of n. What this clarifies, the game could be a growing function of n as long as the value of the game was bounded away from 1 by 1 minus epsilon, and the alphabets that you are all dealing with, where you could put a bound on that also.
What is that C?
Depending on whatever, sorry, I should have said for all games G with, I should have said with alphabet, with answer size C bits. Okay. Possibly there is a constant capital C sitting here. There exists a constant C. That there's a C sitting. It's not like, so this is 96. Then this proof got considerably simplified. It's just like this for close to a decade. Then Hollenstein in 2007 showed the same thing, and what he showed was omega G tensor K is less than 1 minus epsilon by 2 C epsilon square n by C. And there have been subsequent improvements. So several things were there. So firstly, there's one thing which says, let me make some several remarks. One. Firstly, we know that repetition theorem, you cannot get the same strong repetition theorem is not true, but there is some form of repetition theorem is true, and in fact, we get exponential decay. We do get exponential decay. By the way, this is K. No, all papers use N for repetition. N for us has been reserved for the K repetition. Sorry. So one thing is the dependence on C is necessary.
The alphabet size.
Alphabet size. See, that is alphabet size. And these are actually the Feige Verbitsky counterexamples already show this fact. That is, you can, and basically this was the thing that you can, for every K I can construct a game so that you don't see any repetition up to K, around K. Basically you show it by increasing the alphabet size totally, so that you would notice the first time this ever falls less than 1 minus epsilon is when The dependence on C is necessary. So, but the games that we encountered, all the games that we see in the PCP theorem, the dependence on C did not seem necessary. And the games we see that come from the PCP theorem are slightly stronger. There's some property of these games which we have tried to abstract it as a general game over here. If you look at the games that we talked about, the 2 crore game, they were all projection games. In what sense were they projection games? So projection games are games in which the predicate PE right now is of the form sigma 1 cross sigma 2 to 0 1 is actually of the form pi E going from sigma 1 to sigma 2. That is, moment you see sigma 1, you know what is the thing in sigma 2 that you will accept. It had this feature of it was a projective. So these are special type of games, and in a follow-up proof of Hollenstein, Rao observed for projection games dependence on C is not true. There's no dependence on alpha versus. Tell you what the exact statement of the theorem is. Which actually in this case, omega of G less than or equal to 1 minus epsilon implies omega of G is less than or equal to 1 minus epsilon by 2. After C times epsilon n. Actually, it was settled in several senses, but the epsilon square became an epsilon, and the alphabet side.
What is A?
And K, these are all K. Something that is okay here. That's Rao. And this is true for projection games. Okay. The third remark. Small. So right now, this answer, oh, by the way, already Hollenstein and Ra has already answered. But 5K PDM themselves answer our question. But since then, there's been a lot of work which went on to study this problem. Raz showed that actually exponential decay does happen. Hollenstein gave an alternate proof of Rao's theorem. Rao's proof itself was a good 69 pages. Rao's proof was 69 pages. Hollenstein gives a considerably simpler proof, which is about 30 pages. And Rao not only extended it to projection, gave this one for projection game, he also further simplified Hollenstein's proof. Then there was further work was asked to what happens in small value games. What do I mean by small value games? Right now, this one tells you that if the value of the game is bounded away from 1 minus epsilon, then there's an exponential decay. But suppose the value of the game was small to begin with itself, then you still notice decay. You will notice decay. But the point is, you completely ignore because of the suppose the value of the game was 1 by 100 to begin with. This completely ignores that. This makes it a number close to 1 and then says, so it doesn't matter how small this is. It just, such a statement doesn't, all that you care is it's bounded away from 1. It's a little away from 1 and then it shows there's an exponential decay. Does anything happen if the value of the game was small to begin with? Suppose the value of the game was like 1 over log n. When you repeat it k times, does it go as 1 over log n to the power k, or does it go only as 1 over 2 to the power k? You could ask this. These were not proved. So subsequently, so there were 2 works who answered this question in the affirmative. So Dinur and Steurer showed it for projection games. They did show it goes exponentially in the small value, and then Braverman and Gerg showed it general games. Okay. So that's one thing that's there. What else is there about? The remarks. So the proof techniques. The 5K Killian is very combinatorial. Killian is a very combinatorial proof. Ross, Hollenstein, Rao, Braverman, Gerg, these all appeal to information theory. And Dinur Steurer is more sort of analytic or linear algebraic, whichever way you want to call this. So there are sort of 2 different types of proofs. Rather, the main difference being Ross, Hollenstein, and Braverman, Gerg use Pinsker inequality. Information theory will come and Pinsker will come into the picture. Dinur Steurer use cuts and stuff, and Cheeger's inequality is used over there. So those are the proof techniques. One more thing I want to say before concluding this part of the lecture. So there's a question asked about strong parallel repetition. So we know that perfect parallel repetition is not feasible. What is strong? Strong is omega g tensor k. Is it like, so omega g less than or equal to 1 minus epsilon? Does it imply this is 1 minus epsilon by 2 alpha n? That I drop off the epsilon also from the and this was asked actually even for projection games, and
So no epsilon in the exponent.
no epsilon in the exponent. So that it does the decay. So if you think of epsilon, let's think of epsilon as a very small number. So is the decay like e minus epsilon square n, or is it e minus epsilon n? Is that what I'm asking? And Ross, I think, no, in a very much later paper, I think 2010, gave counter example to this with even for counter example even for unique games. What are unique games? Unique games are, so projection games are which, if you know the answer to one side, you know the answer to the other side, which will cause you to accept. Unique is if the projection happens either direction. He actually gave a counter, he gave a unique game for which you will not, gave a proof strategy which works this way. And of course, this seems like just a proof strategy. One may ask, what's the whole point of this? What was before Raz's counter example came, people wanted to know what is the right parallel repetition. Do you have e power minus epsilon n dk or e power minus epsilon square n dk. And this somehow they then related it to what is called so this problem was seemed to be related. In fact, so I will not have time to go into this course at all. But it's an interesting question about what is the size of the smallest volume, smallest object in R dimensions that tiles of volume 1. You want to find what is the shape of volume 1 that tiles the entire Euclidean RD space. Now, certainly the cube tiles the Euclidean space. But among volume 1 objects, the one with the least surface area is not the cube, it's the sphere. So they want to ask what is the thing which has the least surface area of volume 1 that tiles this one. Does it look more like the sphere or does it look more like the cube? So, and the difference between the sphere and this one will be, I think the cube has a dimension 2D in D dimensions, the surface area. The surface area is 2D, yeah. Basically, it's going to be 2 in every direction, it's 2, and there are D directions, you will find a 2D surface area. Whereas this one, the ball, the sphere will have a surface area more like square root D. So it's D versus square. So they wanted to ask what is the best object that tiles the.
But doing tiles at each lattice point, you put an object and
That is, the whole RD can be obtained by translates of these, and there's a translate of this. I'm not going to define it formally. There's a translate of this object that covers the entire RD exactly once, except for the boundary issues. You can define this formally. 1 second, have I? And people wanted to ask whether this best tiling thing looks like a cube or does it look like the sphere, which certainly we know cube does it. And it was said that the reason we don't know the answer to strong parallel repetition theorem is because if the cube was the best, the answer should have been epsilon n. Something close to the cube was the best, the answer would have been like e to the minus epsilon n. If the sphere was the best, the sphere or something like the sphere, then it would have been epsilon square. And because we don't know to show this cube is best, it was not. But then subsequently, Raz's counterexample was lifted to give an object that looks like the sphere. And so it has like object square surface area like square root D, but yet it tiles the entire space. The counterexample was then lifted to give such an object. By the way, and the only proof of this is a non-constructive. Raz's counterexample is a non-constructive counterexample. He constructs a strategy with his non-constructive, so the surface, the body that we construct is a non-explicit object. And here it's interesting if one can come up with an explicit object, which relates back to Raz has a very simple game, which is actually the max cut game on a cycle. You have an odd cycle and it's a max cut game. You have to answer 0 and 1 such that every pair get distinct things. You want to that's the game. This one. And you're asking the k repetition of this. You want to give a strategy that does that violates the strong parallel repetition, gives closer to the perfect pair, and Raz gives a non-constructive strategy, and which strategy is eventually extended, lifted to get this forms. So this has applications to covering RD with forms. A couple of papers. These are very interesting papers. Okay. So what we will do now is we'll conclude this part of the first part. We will take up Hollenstein and Rao's proof, and we'll prove that in the second part of this. We'll give basically, I will give Hollenstein's proof of the parallel repetition theorem. Then I will tell at a high level what are Rao's modifications to get rid of the alphabet size and the projection games. This if we have time, but mostly we will do Hollenstein's So let's pause. Let's take, it's about, what's the time? 11, 14, let's meet at 11:30.
Maybe 10 minutes later, I'll buy energy.
Sure, sure. Okay, so 11:40. Okay, so back to part 2. What we'll do now is actually prove the parallel repetition theorem. Rather, we'll give Rao and Wallenstein's proof of parallel repetition theorem. So what, let's formally state what one. I'm going to state the following for all delta and alphabets sigma 1 and sigma 2. There exists mu, which is mu function of delta, size of sigma 1 and size of sigma 2. And roughly this will come, it's some basically C times delta square by log of sigma 1 times. It's roughly around, that's the order. Such that,
That the sigma 2 is inside the log.
yeah. Such that if omega of G is less than or equal to 1 minus delta, then omega, then let's state it this way, then there exists mu k, then for all k, there exists mu k coordinates which is say S subset of M, such that
The S subset of K.
Such that
What is W?
yeah, same. So what does this, what am I trying to say? So I give you, I say the value of the gain is at most 1 minus delta. Now I'm going to repeat the gain k times. I'm going to parallel repeated gain. And the Wi is the event that the ith repetition is satisfied. So there's a win on the ith repetition. For some prover strategy. I fix a particular prover strategy. Notice this in particular will mean also the fact that
So you're saying on the set S, the verifier accepts.
the verifier accepts. Yeah. That's what that means. That is and.
So here S will depend on the PCP. S will depend on the particular proof.
The S will depend on the proof strategy. So the way the proof will go is, we will see it shortly. You fix the proof strategy, and I will tell you on these yes coordinates, you cannot be doing super well. Okay. And essentially, this is called the Hollenstein theorem. This theorem will be proved by the following lemma, which is, and it should be evident that it follows from the following lemma for all subsets of 1 to k. The probability that, so let's define epsilon I to be for I not in S, in k minus S. Let's define W, and where WS is and of WI minus WJ J minus. So let me write this as
Isn't epsilon a deterministic quantity? Isn't epsilon a deterministic quantity?
it is a deterministic quantity. It's defined for an I. This is expected value over the.
But here you mean when you choose a uniform pi.
When I choose a uniform I outside, yes.
Okay.
The mouthful, but let's stare at this. This is what I will do, and should immediate with this states whatever I want to prove previously. So let's stare at the statement. So basically, what are we, how is the proof going to go? The proof is basically going to go. Firstly, I want to build this set of S coordinates, okay, these set of coordinates, mu k coordinates. How are you going to pick it? You'll first pick an arbitrary element. Any coordinate is equal. Initially, you're going to write. You want to show the. You basically we want to show. Let's look at the graph strategy. I need to show and of I belongs to S. WS. This is one. So if S is actually I1, I2, some I. K minus. Yes. I size of S. Let's call that M.
So in the definition of epsilon I, you have omega G plus epsilon.
Yeah.
So you mean, you basically want to define epsilon I as the difference of probability.
Epsilon I is the difference between how much more it is. This can be written as WI1 times probability of WI2 given WI1 WI3 given WI1 and WI2 and so on. Already WIM given and WIJ J less than. So we want to show this number is small. So the proof is going to show that each of these guys is small. And how does one expect to, so we need to show this is small. To start off with, for any of the WS, this is at most omega G. So this one we have. Now we want to show this guy is also small. And the lemma basically states that no matter which yes you give me, there is a guy, there is on average, there is a coordinate on which it is small. So you take the I1 that minimizes this, choose that to be your I2. Now once again you pick the next guy and you keep doing. I want to claim that from this lemma, the theorem should be more or less true. Notice the lemma deteriorates if PS was already very, very small to begin with, then you're not going to get, the epsilon k is going to be large. The bound on epsilon k will be very large. But if PS is very small to begin with, you already have, so think of, if PS is already exponentially small, then you're already in a good shape. It's only when it's not exponentially small, so PS is at least a large quantity. So you'll typically say probability of WS, using this you can prove, that's the lemma we prove. The lemma says that no matter which cases, there is a coordinate on which it is fairly small. That's one. But how small it is, the small depends on number of coordinates that are still left and this quantity. So this we'll assume is exponentially small. If this were not exponentially small, this is the large number here. And here is where you will sort of use the fact you want to show this. Okay, have I messed up something? No, so I messed up one thing. So there is K over here. The alphabet size, this is in some sense the alphabet size of the K repeated game. So there's a K, it's sigma 1 to the power K, sigma 2 to the power K. And you'll have this quantity over here. Notice that this should lead, I'm not going to show why this lemma implies the proof of this one. It should be clear that we basically say that if WS is not, or if it's already smaller than 1 minus delta by 2 to the power mu k, then there's nothing to be done. If it is, so if it's larger, you get at least 1 minus delta. So if let's assume that WG tensor, basically let's assume that if this is already smaller than mu k minus 1, then there's nothing to be done. If adding one coordinate can only reduce it. If it's already smaller, there's nothing to be done. If it is not, you will get some k times log of 1 over 1 minus delta by 2. Here you will get k by k minus mu k. Now this number you need it to be, it's k, but it's being k. So as long as S is not too large, it's a small number. So you want S to be something like only around mu n or something, a constant fraction of k. Then all of that over there becomes a constant. And that constant will eventually make it like delta by 2. So the original value of the game was 1 minus delta. You will add an extra delta by 2 each time. Each of these products is at most 1 minus delta by 2, and that's how we'll get the entire. Either you have already hit the target of 1 minus delta by 2 per m, or if not, you will manage to set that each of these is at least 1 minus delta by 2, and you will be able to prove this. I'm not going to do this argument, but that's basically from the lemma, it should be clear that the theorem follows.
This will actually even say most sets on expectation.
Yeah, on expect it actually says most, but it's an adaptive fashion. But the first pick, then the next pick, then the next pick. Yes. Yeah. Hmm? Okay. So I'm not going to do it, but it's easy to see that the lemma will imply the theorem. Now, how does one prove the lemma? How does one prove the lemma? Basically, what we need to show is Wi conditioned on Ws is small. The only hypothesis we have is the value of the game is small. So the natural way to do it is you have a k-player game. What you want to do is the only strategy. In fact, this is the only strategy I can think of to prove this game. You have to somehow use this k to. You want to relate the winning on the ith coordinate to actually a single value of a game. So what you would want to do is the following. The provers get just an input for the single value game. They get that input. They are going to embed it in the ith coordinate of the k value game. They fill the coordinates using shared randomness to get a k tuple of questions, but they cannot fill it with an arbitrary k tuple. A k tuple condition that the s coordinates are 1, because that's what we want to show. That is, you need to so what you want to do is the proof strategy is going to be on input so pi on input. What was his input? Qi. His pi is going to get input qi. The idea is to embed. So he's actually going to. Let's write it for prover 1, and then I will do the same thing. P0, Q0. Embed Q0 in the ith coordinate of a k repeated key. That's what they want to do. So what are they going to do? You want to sample. Should have.
So here AC is fixed.
Yes, is fixed. S is fixed. S is fixed. So So they are given only a single coordinate, the two provers. So actually, let me for notation, this Q strategy is going to sort of annoy me. So let me should have done this right at the beginning. The single game looks like this. Instead of Q, so there is Alice is one prover and Bob is another prover. And the single game, Alice sends a question X, Y, gets answer A, gets answer B. Let's stick to this notation. So what I call Q1 and Q2, because I need I don't want so many indices floating.
Definition of epsilon I.
What
was the probability one?
The probability, so I'm fixing a k prover strategy. And the probability is now on the fact that this prover strategy works.
So you already have to verify randomness.
As well as the prover strategy. I'm fixing one particular prover strategy. You can take the best prover strategy for k prover.
As well as the randomness.
Yeah, as well you can assume.
Prover need not be random.
It need not be, but I'm going to fix. So the thing is, I'm going to fix a strategy for the prover and show for that strategy it is bound so much. So this is the single game G. And Alice is going to call convenient to use this notation. Convenient to use this.
So just one question.
Mm-hmm.
So when we are conditioning on WS,
Mm-hmm.
are we just conditioning on the fact that on this set of coordinates the prover answered correctly, or are you also going to condition on the fact that this set of coordinates were queried?
So no. So we have that's what. So on input XY, two provers. How? So this is going to be the proof strategy. On inputs XY to provers Alice and Bob. Notice XY is a sample from the original distribution. It's not from any, it's from the original distribution mu. Alice embeds. So what we want to do is the following. Right now, we'll do all this formally. Embeds this query into the ith location, ith coordinate of a k repeated game, a k repeated queries, such that the provers win on coordinates S. So throughout from now onwards, I'm going to fix the k repeated prover strategies. For the rest of the proof, we will fix these. What do I mean by that? I'm fixing the strategy A goes from x power k to sigma 1 power k, and B going from y power k to sigma 2 power k. So in other words, the underlying distribution is there's a distribution x1, x2, xk, y1, y2, yk. These are the distribution of the questions that's been picked up. Then based on this, the first prover answers a1, a2, ak. The second prover answers b1, b2, bk. Okay. So whenever I talk about capital X, capital Y, capital A, capital B, it refers to this distribution. But I might condition it on various. This is the underlying distribution X, and where each XY, so XI, YI are all got from mu and independent across I. And A bar is Alice on X bar, and B bar is Bob on Y bar. We can assume Alice and Bob are deterministic strategies. We have the best prover strategy for the K prover. This is the distribution we're going to work with throughout the rest of the proof. Okay. But on the process, we will condition this distribution on various events. For example, Wi is the event that the verifier on input xi, yi, ai, bi equals 1. That's one event. Ws is the event. Ws is the AND of Wi, I and S. So there are these various other events we'll be conditioning on. Okay. So now let's return to the proof strategy. What will be the proof strategy? So on input XY, which is sampled according to XY, the original distribution. Alice embeds X into this group of 1 group of 2. So that means take the selection most formally embed x into x1, x2, x. So let's write it this way into x1 all the way xi minus 1 x xi plus 1 xn
XK.
hmm?
XK.
xk xk. Alice should do this xk using and Bob and similarly Bob also embed y into y1 y2 yi minus 1 yi plus 1 yk. So that's called this x bar, that's called this y bar. Using some common randomness R. They use a common randomness R. Okay. Suppose the common randomness R satisfies the following. So what am I? Suppose this distribution that you get, that is firstly Alice and Bob get individual inputs x and y. Then they sample this common randomness capital R from some common source. And then using their respective inputs, that is Alice from her x and the common randomness, Bob from his y and common R, expand this one string into a k input string, and suppose this tuple, this k tuple of inputs exactly had the distribution of x, y, but conditioned on ws. Then suppose we manage to do this, then this will clearly say that probability wi given ws will be less than or equal to omega g. Because this is a poor strategy to answer a single game. They're going to expand it this way, then use the one. So if Alice and Bob could do this, and of course, then they will have to I only talked about the first part, then they will answer according to that Alice and Bob. If they do that, embed and then answer. According to the A and B. Then, and if this common randomness had this property, then we have managed to show Wi given Ws is actually less than omega j, because this is the prover strategy for the single player game. But there are several things here which are if. Firstly, why is there a for this to happen? Several things should be true. There must be a coordinate I in this, such that the marginal of xi, yi, even after giving Ws, is the original distribution. Otherwise, this is not the game. Firstly, there must be a coordinate I which has this feature.
Actually, we are showing that the average over all the i's of epsilon I is small.
Yeah,
So it will be so that the expected.
yeah. So eventually, I will only be able to show this. So this will prove the statement I have below.
So that this particular epsilon I is small.
This particular, in general, I won't be able to show this. I will have a statement stating that there will be an average over I, and I will show this. If I had this, I have this particular. If I have this, if I have that common randomness satisfies that magical property there, which I don't know how to get.
Is then you get this particular epsilon I is.
Then this particular, this is which is all I wanted to show.
You wanted to say expectation. This is away from the theorem, but
Which is suffices for the theorem, but we will see why I will actually go for expectation. But let's have this. Yeah. We don't have this. At the very least, in this, we need on the I coordinate, we need that the distribution, even after conditioning on Ws, should be the original distribution. And furthermore, now notice that if we had not conditioned on Ws, Alice and Bob can easily extend their inputs using common randomness. But because you conditioned on Ws, the two inputs are got because of the way the Alice answers A1 and AP are there. The two inputs have got extremely correlated. It's unclear that Alice can extend her input of her own and Bob can extend his input of his own, such that they need to expand this out to exactly this distribution. It's unclear you can do all of this. Question is, firstly, we need one particular I on which such a thing is true, and then we have to choose an R for which a common randomness for which will enable Alice and Bob to do this. What we will show is we don't have such an I. There will be various errors that happen. We will show that for a particular I, certain errors, that is the marginal on xi yi condition on Ws will be close to xy. And furthermore, I have come up with a random variable which will almost give this property. Therefore, what we will have is not, we won't be able to show this, we'll be able to show Wg plus the error quantities for epsilon I.
So, but it's almost a capital R here because all you are saying is that the marginal distribution of the I coordinate condition on Ws is identical to mu.
Yes.
Certain capital R exists, we can only place it to, right? So couldn't we place this without capital R?
You could state this at this point without capital R, but the construction I will give is they will first sample a common R together. So there will be multiple errors in it. That is, they will have to show the way the algorithm will work. If they will first show that there is a magical R that has this property. Now the question is, can they even sample this magical R? This magical R, unfortunately, the way we construct it will be a function of small x and small y. It will not be a function of, right now it has been independent. It has been independent of small x and small y. We will show that despite that, we will show various things out of it. The reason of doing this is there will be multiple parts. Alice gets an input x, Bob gets an input y. There's a capital input R here. And we show that there is a third party who knows x and y, who can do everything correctly, who can get all of this. And Alice only has R and X, Bob only has R and Y, and yet they all look alike. So there will be several error terms, and those error terms will be what will be epsilon I. And then we'll show that we won't be able to control just epsilon I, but we'll only be able to control the average of them. Therefore, one of the i's will be small. And On the face of it, this is a very natural. This is, in fact, if I want to do this, is the only way can do this. The R might seem artificial at this point, but soon you will see R is also natural. If I want to do this proof, you want when you're proving upper bounds, you might assume that the provers are randomized, and you might help them to come up with all sorts of common randomness, which will help them to get their inputs together. Okay. So our very first thing is, why does there exist an I, coordinate I, in which xi, yi has the same distribution as the original distribution? Conditioned on WS. Conditioned on WS. So let's first ask that question. Let's first just ask that question. So I'm going to do a whole bunch of. So we'll have some exercises in probability for the next 10 minutes. And basically, the heart of it is, if you hadn't conditioned on WS, certainly every coordinate is like that. Now, WS could be leaking information about a particular coordinate a lot, and it might completely change it. But we do know that WS is a dense event. If WS was already very, very small, we didn't have to care for it. WS we know is a large probability event. When you condition a large probability event, when you condition a product distribution on a large probability, what will show is, and so we have a product distribution, say U1, U2, UN. Each UI is X, the pair Xi, Yi. You condition a product distribution on a large probability event. What will show is, on average, each of the guys that you have are actually close to what was there before, because this is a large probability event. There will be some of them which will get skewed very much, but on average, a UI conditioned on the event E will be similar to, so UI conditioned on E will be close to UI itself. And this is a very variable statement. We will use scale divergence. Information theory will come extremely useful. So basic probability primer, rather information theory primer. Let's do some. So I'm going to, the heart of it is going to be what's relative entropy or scale divergence. So U and V are two distributions. Then the relative entropy between U and V is defined to be summation probability. So U over some set, say M, U and M, probability U is U times log of and the two things which you will take without proof, is first is DUV is always non-negative. This happens to be and you can use this essentially a Jensen of a particular quantity. You can eventually stare at this definition, and it will be the convexity of some quantity will show you that relative entropy is always a non-negative. And the other thing is Pinska's inequality. So this is one metric you can define between them, and another metric you can define between two distributions is the L1 metric, or the total variation distance, which is max over all subsets of M probability U in M minus probability B in M. Okay. Yes. U in T minus probability B in T, which is also half of summation over all U and M. 1 probability U equals U, absolute value minus. That's the L1. That's what that's a total variation distance, which is half the L1 metric. In principle, if you draw the histogram, so this is 0 to M. These are 1 to M, all the elements, and this is 0 to 1. If you draw the two histograms, this is say for U and this is for V. This quantity will certainly be equal to this because both the sums under both are 1, and each one is that quantity, that each of them is the each of them is exactly the, this is the U minus V, and so is this. The mass of that is exactly the mass. Okay. Pinsker's inequality sort of relates these two notions of distance against each other. It says if the relative entropy is small, so is the L1, the total variation distance. In particular, it says D of U given V is certainly U minus V squared. Okay. No, that's
Is it two real?
huh?
Is total variation distance half square root L1?
Depends whether you're talking about L1 norm or the total variation distance. In this, I think it's exactly this.
Then you also get under base of
Huh?
already get under base. Yeah.
Base, yeah. Right now I'm going with log 2. Let's stick to this. There might be a constant, but let's stick to this for now. So now I'm going to make several claims. The first claim is exactly, so V is some event, V is some random variable, E is some event, and we suppose we know probability of E is not too small an event, it's at least 2 power minus D. And let V tilde be the event V conditioned on E. That is, what happens to B when you condition that the event has happened? It's the new distribution that you get. Let's ask then D of B tilde versus B. How much is it? I want to claim this is never more than D. Proof of this is just follows from the definition. B tilde given P is what? It's summation over all U, probability V equals V conditioned on E times log of probability V equals V conditioned on E by probability V equals V. That's just the definition. This is what? This is summation U probability V equals V conditioned on E log of, let's expand this out. This is V equals V and E by given probability E. So it's log of 1 over probability E times probability V equals V and E fair enough. This is a number always less than or equal to 1. Therefore, I'm going to upper bound it with 1. So this is at most 2 power D. 1. You get a D and that's a probability. So you just get D. Okay. So that's another claim. Okay.
Sorry, what happens? So probability of E is where you get 2 to the D.
Yeah.
Probability of B and E.
By probably that's upper bounded by 1.
That's it.
So this whole quantity here is upper bounded by 2 per D.
And the thing outside you're just summing over.
All, yeah, that's upper.
So E becomes more likely as D increases, and we're saying that
E becomes
E
more
more likely as D decreases.
Yeah, so if you are conditioning on an event of probability 1, nothing would have changed.
This is a robust word.
This is a robust version of it. It says how much can change. If you are conditioning on a very large event, V tilde and V cannot be too very different from each other. This E will be our eventual WS. Possibly we'll add some more, but it will be something like WS that we'll do. Suppose you had two distributions. These are not necessarily product, but one of them was product. This was actually a product. Then I want to claim D of V bar U bar is greater than summation D . Actually, for want of time, I'm going to skip the proof of this. This is just open this out, write the difference between these two quantities explicitly. Use the fact it's product distribution, that is product of the bottom factors or the top doesn't necessarily factor out. And write the difference between them. If you write the difference between them, what you will get is relative entropy between two other distributions. And hence, this is non-negative. Basically, the proof is this.
Using the concentration inequality.
Huh?
Using the concentration inequality.
Oh, it was okay, fair enough. Yeah, okay. So now, okay, with this, we will be able to do the statement that we wanted to prove. That's our first proposition. So U1, U2, UN is a product distribution. So this is like our pairs x1, x2, x1, y1, x2, y2, and xn, yn. And E is an event such that probability of E is greater than 2 per minus D. Then I'm going to look at the expected norm between the distribution UI conditioned on E and just UI. I want to claim this is square root D by N. And I claim, well, this is basically, we have everything to do this. So expected I mod UIE minus UI is less than or equal to. So let's put square outside. U and E minus U square. This is convexity. I'm taking the square inside the expectation. That's convexity. Convexity of square. Now let's go to Pinsker. This is D of UI conditioned on E. UI, that's Pinsker. This is equal to 1 by n summation just writing. Well, now you'll apply the one of the claims that we proved. This is at most 1 by n d of u bar conditioned on E u bar. The bottom is a product distribution, the top is not a product, not is an arbitrary distribution. Right? But this we saw as at most this is one, these two are claims which we proved. Okay. In fact, this is sort of this lemma is sort of the workhorse for the whole tool. This is the reason that even though we are conditioning on this event, because it's not a too small a probability event, on average, the UIs post conditioning on the event WS still look like the UIs in the when they were the product distribution. So there is a I which is good enough for us. We don't know which I, but they are good on average, and that's what we'll be heading towards. Okay, so this at least answers the first question in this of our proof strategy. It tells us how to do the embedding. It says an average I is good enough. I can embed the average. But now I need to tell you from the I, how can I expand to filling the remaining k coordinate, k minus 1 coordinate independently, not to. Notice it's easy to do it. So there are, think of now 3 parties, PA, PB, and a party which knows both the inputs X and Y. So now somebody has told them this I coordinate is good enough. The input distribution mu, and even after conditioning WS, they are unaltered. So you put this in this side. Now each of the parties, the ones which knows Alice, Alice who knows only X has to expand this to k coordinates. Bob who has to expand this has to expand into k coordinate. And let's think of another third party who knows both of them. It also needs to expand to 3 parts. The third is just for the sake of our understanding. The third can certainly expand this out to k coordinate because he knows X and Y and he knows how to fill this. But Alice and Bob don't know how to do this because they have to ensure that when they extend it, it should still come from the xk and yk should come from xy conditioned on WS.
So to clarify, if the conditional distribution on WS was product is good linear.
If the conditional distribution on WS, if WS ensured that there was a product,
Then this is trivial.
then this would have been trivial. So the point is, we will now try to make Alice and Bob sample something so that given the sample, suppose firstly, we'll break this task into 2 ways. We'll show that there is a particular random variable such that given this random variable, what they have to sample becomes product. And then you will show, so that's one. Of course, you could say this random variable could have been what they should have sampled from it. But then you will show that this, and you want to say that so there's a common random, this is where R is going to come. So you want to get a random, you want to lay your hands for a random variable, so that given R, Alice can do it and Bob can do it independently. But furthermore, this R is going to come from a distribution in which there are going to be 3 different views of this R. R from a person who has both X and Y in the hand, or from a person who just has X, or from a person who just has Y. We will show that these three distributions, that is the corresponding distribution of R, the R from all these three distributions will actually be close to each other. This will tell you that even though Alice is going to sample from a different distribution, Bob is going to sample from a different distribution, what they'll sample will actually be the same quantity with very high probability.
That is the third properties are statistically
Close to this. Okay, so that's how we are going to design. So we have two tasks now. We have to first now come up with an R, so that given R, it becomes a product. But this R should also have the feature that this R should be a distribution such that R given small x small y, the distribution of R given small x small y, you're looking at three distributions now. R given small x small y, R given small x, R given small y. These three distributions are actually close to each other. We want an R which has both these features. So now we'll construct a random variable R.
Don't we just need R given X and R given Y to be close to each other?
R given X. Actually, that is sufficient. It's just that the whole proof will go with the person. We'll relate everything to a guy who knows both of them. That will be the truth. And so we'll say everything works according to that.
So now we are fixing I.
So I have not fixed an I per se. That I'm saying an average I has this property. There will be errors which I'll accumulate here also. There will be average errors here. Eventually, we'll say that the average error, error for an I on average is small. Therefore, there will be one I that has.
Now when we are constructing R,
for every R will know which I you are working with. Want to construct an R that is actually an Ri. If knows this one, so R of I, random variable. A random variable R, which actually R of I, as you have said, such that one for each R in support of R, we have that X minus I conditioned on WS and R equals R. So basically, what I want is XY minus I. Now by this I just mean the whole thing. This one conditioned on. That's right. That's right. The whole X bar Y bar conditioned on XI equals X. YI equals Y, WS and R equals R is actually X conditioned on XI equals X, WS and R equals R times Y conditioned on YI equals Y, WS and R equals R. So you want this product to happen. That this distribution on top is exactly the distribution below. This is certainly easy to get, but I want the other property that the distribution of R given XI equals X and YI equals Y. The distribution of R just given XI equals X and the distribution of R just given YI equals Y are all close to each other.
So now you are forgetting about the original distribution. What? in this condition, you are not considering the original distribution.
I am, no? So everything is.
One your condition is not xi, then the
Hmm?
condition distribution of r given you does not.
No, I have not told you what R is some other random variable, correlated random variable I have to construct. Of course, the xy given mu is sitting there. That should be, so the R should be useful to construct this. I have to construct an R which has this property. Okay. So what is such an R? Actually, even before going to such an R, let's ask the following statement. Suppose these three distributions were close to each other. There's a truth correct R. This R, this is R condition xi equals x is what Alice sees. R condition y is what Bob sees. Suppose these are actually not just close, they were actually the same distribution. How do you ensure that Alice and Bob, it's not sufficient that Alice and Bob have the same distribution. They have to sample, because the previous step requires that they have the same copy of R. It's not that they have the same distribution R. The previous one assumed that R equals R. It's the same R equals R in both cases. But Alice can't sample from her distribution of R and Bob. They can't do it. They need to get an identical copy.
So we got a public one protocol.
So how would you? So let us. How do you sample from such a thing? So how do you? Okay. So if it's a common distribution, one can easily think we will just use but the point is this Ri. Suppose.
So you want to use shared random.
Shared random. The easiest way is you think of the things in the shared random, the samples from this common R. And then Alice and Bob just read it out. But suppose let's make it a little harder in the sense that this R is not something that they knew up at the very beginning of the protocol. That is, the shared randomness is not coming as sequences of R. That is, they have come to some step at which point Alice has a distribution, Bob has a distribution. They have come to this step. That is, this is not something that they knew upfront. That they could not arrange the shared randomness to be sampled from this. They have come to a place where Alice has a particular distribution, Bob has a particular distribution. These two distributions happen to be identical distributions. How do they now use shared randomness to sample? So Alice has to sample from this distribution, Bob has to sample from this distribution, and when they sample, they should exactly sample from their respective distribution. But their copies should also be identical. How do you ensure this? Once again, using shared randomness.
So even before the game starts, for all possible distributions, we will assume they have taken identical samples.
Yes.
And then, so they know the value of S, so they know from which distribution to sample from. So they just.
How a distribution? How do they know?
No, so before the game starts.
Yes.
So they know all possible for each S and each I. There is a distribution R.
So forget about I and S. There is there's just one support size M, and Alice at some point gets to know, lays her hand on the distribution. That is basically she gets P1, P2, Pm. Bob gets Q1, Q2, Qm.
So we get a public coin protocol.
Yes.
So then can we just average over this and say that there is a deterministic protocol?
What do you mean?
So
No, I don't care about determine. I don't care. You can construct randomized protocols. You can construct. So the task is the following task. The task is the following task. There's random strings, random things in the sky. Now Alice is given a distribution. Basically, she's given a sequence of strings P1, P2, Pm, bunch of young probabilities with sum up to 1. Bob is now given Q1, Q2, Qm, we also sum to 1. Now they need to sample an element from their respective distribution. They have to sample a perfect thing. And this sampling procedure must be such that if the two distributions are identical, at the end of it, they must produce the same sample. They could use common randomness.
Okay, so then you add the numbers P1 to Pm on a line.
Okay.
And sample a uniform R and see which interval it belongs to.
Okay, so that's you are saying I will assume a priori ordering among 1 to m, put this on a histogram, and then pick. Yeah. Okay, so this one I agree that works. Now suppose I gave you P and I gave you Q, and I told that these P and Q were not identical, but they were close to each other in total variation distance.
So there is sensitivity.
What's the same strategy?
So, and divide 0, 1 into intervals. So
Mhm.
the length of the I, Bob will divide 0, 1 into intervals.
Yeah.
The length of the I interval is Pi, and Alice will do the same thing,
Mhm.
and then they will sample a random point. Now, what is the probability that the points are different? That is exactly when it is in one of the border areas. That's around summation and absolute value of Pi minus Q.
No, see, you want, I don't know how to do it with summation Pi minus. Summation Pi minus Qi, I'll get it. Okay, so the picture, the way I want to show the problem, I want to do is now the following sample, correlation sampling. This is called correlated sampling. This was stated a little more general. I want to state that suppose there are L distributions E naught, not that. Let's call it L plus 1 distributions P0, P1, P2, Pn. So, that's right. Let's write it this way. There exists a sampling procedure. The theorem is the following. Sampling procedure, let's call it A, which has a filling, such that for any L distributions, L could be any number, A naught, P naught, PL, I give you L distributions. Now, you run the sampling procedure on each of these separate distributions, each of these distributions separately. That is A of, then let BI be the sample obtained by running A on PI. So the sampling procedure gets us input a distribution. Based on that, it's going to run this. That's the following holds. One, BI is identical to AI for all I 1, 0 to L. Probability that BI is not equal to B0 is at most 2 epsilon I, where epsilon I is the distribution, is the BI is sampled according to P0 minus P9 and 3 probabilities all BIs are identical. Is at least 1 minus
Doesn't it automatically follow?
it follows. It follows. Yeah. Yeah. Yeah, that's how I want to state it. And the idea is just the proof of it is essentially what Miguel said. So I'm going to write it this way. So let's assume that there's an ordering among 1 to m. So let's look at this. So there are these various distributions lying like that. And let's think of the random samples in the slide. These are the CDFs of the various things. So they say this is the distribution P1 and the distribution P2. Use common randomness as uniform samples from m cross 0, 1. So think of the common randomness as samples in this square, in this rectangle. And the you have a particular distribution pi. The movement, so you have the sequence of movement is common random, this point falls under the curve, you output that point. The sampler is the following, which is just similar to what you said. In fact, I think it's identical to it. The algorithm A is this on input. So what do you get? You get I1 comma alpha 1, I2 comma, it's an infinite string like this. This is the common randomness. I say T comma alpha T. Output J such that J, which is J such that output JT such that T is argmin of over all T such that alpha T is less than or equal to P of IT. It's the first time it falls under this, you output it. That's the sampling. It should be clear that this samples exactly, each one of them samples exactly according to the right distribution. And furthermore, when are two distributions going to be different? When are they going to be producing a different point? Only if this point either falls there or there. Otherwise, so that's exactly the 2 epsilon I that comes to. So this picture is the proof of this fact. By the way, so this is correlation sampling. It was once again, it's a very simple fact, but this was discovered multiple times in the theory literature. It was discovered the broader ones in Holenstein, and Holenstein's contribution to simplifying Raz's proof is basically the use of this lemma. This shrinks the Raz's proof by a good 25 pages, the application of this lemma. So it's sometimes called Holenstein's lemma, but then it was realized that it was existent much before Holenstein's sampling.
Is scale divergence and all this is from scale divergence idea is from Raz's proof.
Which one? Scale divergence is Raz's proof. Scale divergence is Raz's proof. Okay. So this tells you that at the very least, if 2 is given to us, so okay, what's the strategy right now for us? There's an error that's going to accumulate for us. One error that has accumulated because of the xi's and yi's conditioned on ws are far from xi, yi. Then that's one error. Then suppose we magically designed this R. Suppose we had this. Then we would show that there's an error over here too. Then we say an error delta I between them. Now you will notice that but for this error, this works perfectly. This is exactly what we wanted to show.
There is some error in the correlation stem.
Correlations are correlation. Yeah. So there will be three kinds of errors. So that error is just going to be this epsilon j. So we will show that what's going to happen. We are going to assume that we'll run this protocol. We'll first build an R. We'll run this protocol this way. What are the errors? First error is this fact that xi, yi is not the same as the conditioning on E. Then we construct the R that we construct has a property that the guy who knows both parties works perfectly fine. But then we'll say that Alice only has R of xi, it has this skewed, slightly varied distribution. But then, despite that, because of the correlated sampling, the sample that Alice gets will be with very good probability equal to what the person who knows both of them gets, as well as Bob also gets. So Bob and Alice and Bob also have, but for this 2 epsilon I probability, they have got the same sample which the person who knows both the inputs know. But now once you have this R, because it's a product, they can fill and the rest of the proof will go.
So in the first one, this is 0 errors.
The first one we want product because here we are not saying this is any, we are going to get an exact product distribution. Okay, so the rest of the proof is to design a random variable R which has the product behavior and that these two are close. Okay. So how do we construct the random variable R? So the point is R should help you to, so conditioning on WS is what made this extremely dependent. It's not the fact that there was a product behavior has been killed because of WS. So you want to put in R such that this product nature is sort of restored once we know R. So, and so this choice of R is exactly what Raz had chosen, and Raz credits Rasborough for inspiration for this choice of R. This R is inspired by how Rasborough handles the proves disjointness in the communication complexity. So he
The corruption.
the corruption bound version. So R. So what's R? So we are conditioning on WS. WS has brought in all sorts of correlations between the two parties. So first thing what we'll do is let's further condition not just on WS but the answers on the S coordinate for Alice's side and Bob's side. Once we know that, notice that the answers are just dependent on Alice's inputs and Bob's inputs. Now, once these are just functions of Alice's k inputs, Bob's k inputs. Now, WS is just now a function of these answers. So so R is going to have several components in it. R is going to be answers for Alice and Bob's input on coordinates of in S, that is AI BI for all I in S. We're going to give this.
Then both Alice and Bob will use.
We are going, we are constructing R. We will then figure out how to sample from this R later. This R is, we have to do two, this R is going to be constructed in such a way so that one, given R, you should be able to do the product. And two, the R should have this feature that R given XY or R given just X, R given just Y, these are all opposed to each other. So the reason I'm giving this is once I give this, I don't have to now, the even WS is just a consequence of this. I don't have to further condition on WS. A is the B. So sort of, once I have these are answers, these are the answers, and you don't care now is it winning or not, because now this is just the WS is just a function of these AIs and BIs. Okay, so we'll first put this
But the sampling from these two must have been not really.
Huh? No, I haven't told how any of these are. This one, we'll have to look at all of them.
Yeah, the formation of these now is not a product of history.
Is it a product? It's still not a product, no? Because a single answer to a coordinate could have depended on other questions. The answers to these questions are not just functions of just their AI is not just a function of xi. AI is a function of x1 to x. It's still not a product thing. To make life easier, we will put in all the questions for the I coordinates. Let's toss. By the way, we still do not know if it's winning at this point. I need the questions also to know what they are winning. So let's put the questions for coordinates in S.
So it is predicates.
I in S. The queries, yeah. Xi by S, we put this also. So now WS is, you don't have to add the event WS because now given Xi, Yi and AI, Bi, you know whether Wi has happened or not. This is just to ensure that I don't have to carry this WS which is correlating Alice and Bob. There are two types of correlation happening. One is correlating Alice and Bob, and one is correlation between the coordinates of Alice, between the coordinates of Bob. The first thing I want to do is break the correlation between Alice and Bob so that they can do. And that the whole point of that was to do this. So the only correlation that is not happening is among the coordinates Xi, by the way, even the original input, Alice and Bob were correlated, Xi, Yi were correlated. Yes. So I want to now ensure that now the questions outside yes. Yeah, I want to ensure that Alice can sample from incompleted, Bob can sample from. So what we will do is for each of these coordinates, it seems strange that this will work. This is what Rosborough uses and Rosborough uses the same thing. For each of these coordinates, we will sample a question randomly. We'll either sample Bob's question or Alice's question and give that. Certainly, one of them is chosen. The other one has to sample only from the corresponding margin conditional distributions, and hence they can do it independently. So let's stay. So the next. So I'm now going to give a random Alice Bob question.
So what do you mean by Alice Bob?
The two provers I'm just calling, so calling them P1, P2, I'm using indices. Alice and Bob are the two provers.
So for each J not in S, you need to fill in both AJ and BJ.
No, that's for the answers. For not in S, I haven't yet. I'll finish a random Alice Bob question. That is, we will come up with VI, I not in S. Is for each VI is a uniform random bit from 0 to 1, or let's call it from A and B. It's uniform, it's either Alice or Bob, and TIs, so this is I not in S, and TI, I not in S, TI is said to be equal to Xi if Vi equals A and Yi if Vi equals B. So that's what I give. So it's going to contain these VIs and the TIs. VIs tell you which of the queries I'm going to pick at random, and once I pick it, I tell you which of the queries.
What? So take any I not in S, you need to fill in the values of both Xi and Yi.
Yeah.
You are saying you just fill the value of one.
I will give a common randomness 1. If I give that, then there is nothing to be filled. If I give Xi and Y.
Oh, okay. This is part of the information.
This is part. So no. Eventually, they have to fill in. They have to give the whole XK. They have to fill. I want to give them some common randomness so that they can now independently go and fill the K tuple themselves. So how much can I give? Is a question. Of course, if I give XK and YK, if I give X1 to XK and Y1 to YK as a common randomness, they can fill it up. But the point is, this is not a variable for which I can show property 2.
Oh, the property 2 is the constant here. Yes.
This property is going to be difficult for me. So we are now going to show this instead. We will show this. It's unclear. This also I'm giving you so much amount of information I give you. But the point we'll notice is there will exist a coordinate in which this so okay, so this is first thing, this is going to be the random. So R is going to be this whole object. R is going to be AB restricted to S, XY restricted to S, and this VT restricted to S complement. That's what R is going to be, this gigantic beast.
So here to clarify, Xi is a sample from W conditioned on AB X1. So in TI is a sample from. So the joint. So first we select all the PIs, and then the T's you select will be the conditional distribution conditioned on AB and XY. Is that right?
No. So there is only one distribution that we have been working with, which is this distribution. That's the distribution we are working with: x1 to xk, y1 to yk, and the corresponding answers a1 to ak, b1 to bk. Now everything else is going to, I'm going to use this to come up with samples. So how am I going to construct R? The R is constructed this way: R, the random variable R. I'm going to give out AB on all the S coordinates. I'm going to XY also, I'm going to reveal all the S coordinates. For the remaining coordinates, I'm going to sample some more random bits. For each of the remaining bits, I'm going to sample a random bit, which tells whether I'm going to reveal Alice's question or Bob's question, and then reveal that question. That's it.
The clarifying, R is a sample from the conditional distribution of WS.
R is this sample, and then WS is, if I now further sample and WS, that's just a function of AB, XY. That's just a function of this. So then I will, the fact that R is going to be a sample from this object, R is just this distribution. I will have to eventually look at R which are coming from R conditioned on WS, but that's just a function of this. That is basically, if you pick an R and it happens to be not, you can look at R and see whether WS is satisfied or not. If you sampled it, you will just reject it and you start with a new R.
So you do rejection sampling.
You will do rejection sampling on that, yes. The proof won't go that way. You can do rejection sampling. The point is, when you sample R, you will know. So you will know whether WS is satisfied. That's the whole point. This is put here so that WS satisfaction can be checked right away. The correlation brought due to WS are not there anymore. Okay. Given this, so this is R.
So the first property is now satisfied.
The first property, it should be clear actually from this R that you can actually independently fill the. Let's check that that is satisfied.
The moment we set the sample little r from capital R, we have already fixed the xi's, yi's in the set S.
Yes.
The rest of the set we have fixed one. In the rest of the coordinates, we have fixed one of these,
Yeah.
and the other we can sample it in one.
Yeah. Other, so that's right. That statement. That is that statement. I want to claim this should be true, evident from what we have.
So the second
Yeah, the second part will require some work, but it is not. Question is, do I want to do it now or should I postpone it to next class? Can I take 10 minutes and finish off, because it just follows from what we have already. So this should be clear. And the point is, it might seem as if WS causes confusion, but the point is WS is a property of R. Therefore, this having this extra feature here does not cause me. Once I picked a particular R, either WS is satisfied or not satisfied. WS doesn't cause any further. The reason R is that you put in all the questions and answers in S coordinates, if you ensure that this putting the WS there is not going to cause me any further issue. Okay.
So why there was a third part about S bar in R? Why was that there?
So that Alison dot can easily.
No. How if that's not the case, how do they sample? If I had not given S, if R did not have VT, how do they sample?
So that part is just going to tell you Alice's questions on some coordinates, Bob's questions on some coordinates.
Yes.
So there's some space to
And
fill.
you also need to get the answers.
So let's look at the previous. So there is Alice's case. Initially, these were all independent. X1, Y1, X2, Y2. I is not important at this. The way I said I is not important. Now, Alice from this can produce the sequence A1 to AK. Bob from this can produce the sequence B1 to BK. Okay, actually, I is important. So there is this one coordinate which they both have. X and Y. Both have. Now, let's assume that these are this is the S coordinates.
Okay, no, you don't need to get the answers.
These are the S coordinates, and these happen to be. Let's say these are the S coordinates. These happen to be the coordinates Alice is getting. These happen to be the coordinates Bob is getting. So now basically R is this, and this. Now the point is, because of this, because I'm giving this, I have already there's a distribution that I have to enforce on these guys. Because the origin, if A was were not given, these were product. Because this has been given, there are distributions that have been set up. The correlation has been built among these guys over here. Similarly, because of this, correlation has been built up among here. But what I want to say, but this A is just a function of this guy. This is just a function of this. B is just a function of this guy. And the WS has we have lost WS now because of the correlation. So now Alice.
It is condition from the sample from the condition.
Alice just needs to sample from. Look at Alice will just sample from the conditional distribution that she sees this X and this A and fill this. And Bob will just sample from the corresponding. And notice that this is exactly the right distribution we want.
So there's no edge where they both end up sampling.
They both, that's the only edge XY, but that's come from the right sample.
It is using close to quality.
So because that came from the XY here. So there is no edge which you have left in which they have to sample together. The only edge is this XY which they put XY. Every other edge has been R has taken care of.
If there was an edge, there's no way of
doing this. Because Alice's answers would have weirdly correlated Bob's answers and stuff.
Yeah, so I think this is the part that I missed. The fact that this choice here depends on stuff that's happening on the leftmost cloud.
Yeah.
The choice here depends on Bob's.
No, so this, so first let me put the picture here. We could have this picture here. So then I will actually draw this picture and break now because it might take another 15 minutes and it's not possibly worth. So there's X1 to, so let's call this X1 to this one. There is Xi, which is X, Yi, which is Y, and then there are others. So let's break the picture into A parts, this is the green part. The green part is the S part. Then there is Alice's answers, which is A1 to AK. And there's also a green part over there. There's Bob's B1 to BK. There's a green part over there. And then there is an orange part here, which has been released, and an orange part here. So the only edge which is cutting across is this edge. Every other edge you have broken off. And that's important. So now I want to claim that basically the proof is claiming that Alice can sample the yellow part using her information. Bob can sample the purple part using his information. That's what they do. And they are sampled from the green, then there's this orange. And that though this whole thing is R. Easy to see. Alice can sample from the appropriate conditioner. Similarly,
So now we need to extend that our condition to next one is statistically close to one.
yeah. So now I need to show. So we will defer this to next one. The next lecture. We'll show that the distribution of R conditioned on xi equals x and yi equals y, and R, sorry, not and WS. There's a WS going on over here. Now I can't remove the WS. This is close, epsilon I close to R xi is x and WS, and similarly it's also epsilon I closed R condition on yi equals y and WS. We will show this.
This statement is not based on some sort of a regularity of that.
No.
We have no control on that. The graph could be very non.
Yeah. By the way, the proof of this is almost identical to the previous. This one is going to be almost the same jugglery will happen. It will be 15 minutes, but it's going to be jugglery. I don't want to do it now. We'll do it at the beginning of next lecture and then go on to the next. Everything we already proved. There's nothing we haven't yet proved. We'll do this next lecture, which will complete the proof. So let's start with this.
Epsilon will be negligible or like some d by n?
Epsilon won't be negligible. It will be like delta by 2. It will be a epsilon won't be negligible at all.